I, which is the square root of -1. And if we but that one, if we take I and we multiply it by itself, I times I, we get -1 or I squared, and that ends up back on the real axis at -1. If we do I times I times I, that's I cubed, and I cubed appears down there at -I, so it's back on the imaginary axis. If we do I times I times I times I to the fourth, we come right back around to this spot right here, which is I to the 0, which is just +1. So the very first big takeaway is that as we multiply by I over and over and over again, it's rotation. We're rotating counterclockwise around the Argand plane or the complex plane. If we take a look at these 4 points and we connect them all together, we get a square. And find the area of that square in a very roundabout way by finding each of these 4 squares one by one. And we can do that by using an area of a triangle formula. So most of the times we use this standard one, a equals to 1/2 base times height. But there's another formula that's less frequently used, which is a is equal to 1/2 AB sine C, which is that if we know 2 sides of a triangle and the angle between those 2 sides, we can calculate the area of that triangle. So if we take the area of this first one here, we could say the area of the first triangle is equal to 1/2. Each of the sides of that triangle here and here is both 1. So we get 1 times 1. And then we take the sine of the angle between them, which is 90 degrees, or pi over 2. And we'll put pi over 2 here in radians, because this will become useful later. And so if we wanted to calculate the total area of this square, what we could do is multiply that result by 4. So the area is equal to 4 times 1/2 times 1 times 1 times sine of pi over 2, which is just 1/2 sine of pi over 2, like that. And we have now calculated the area of that square, which we could just look at and do very easily. It's just 1 times 1, so 1 by 1 square. Is that true? Actually, that's not true. Um, but we get the area of that square. So that would be 2 times sine of pi over 2. Sine of pi over 2 is 1. 1 times 2 is 2. So the area of that square is 2. Another thing that we could do is that we could increase the size of this polygon. And you're probably starting to see where this might go. Let's say that we remove this polygon, as we see right now. And what if instead of 4 points, we doubled the amount of sides to 8? So we added in a couple more points, maybe here, and here, and there, and there. We can already see that just going from a square to double the number of points, 8 points, an octagon, that we're starting to get closer and closer to a circle. The question is, how do we find those points in between the other 4 points? So if we think about it, that point in purple between 1 and I is halfway between those two. Or we could say that if we do 1 times I and it turns into I, there should be something that if we are here and we multiply it by itself, it'll turn into I. So we have something times something is equal to I, like that. And that should make you think, hopefully, of a square root operation. So we know, for instance, 2 times 2 is equal to 4. So if we're trying to find out what this unknown number is, we simply just take a square root of both sides, and that gives us our answer. So we're trying to find the square root of I. So this mystery number here is the square root of I, or I to the 1/2 power. Kind of weird to take a square root of an imaginary number, but it's exactly what we need to do. And if that one is 1/2, then it's not too hard to guess what these other values are going to be. This one's going to be 3/2, and 5/2, and 7/2. So it turns out that all the points as we move around this polygon are just I raised to different powers, which is pretty cool. Once again, we can ask the question, what's the area of this shape? And to do that, we can once again break it apart into a couple different triangles. In this case, we're going to have 8 triangles in total. And we can use the exact same process as we did before. And we can say, well, the area of one of those triangles is a side here. And we have a side here. And we still just have sides of 1. And the area, the angle in between, is now an entire circle, which is 360 degrees divided by 8, or 2 pi in radians divided by 8. And so that's 45 degrees, or it's pi over 4, like that. So we can say the area of this triangle is 1/2 1 times 1 times sine of the angle, which is pi over 4. And if we wanted to find the total area of all of those added together, we could just do 8 times that result. So 1/2 sine of pi over 4. And once again, we could increase the number of points and the number of sides. And the more that we do this process, the closer we get to approximating or actually turning into a circle. Let's make it a little bit more visible. We can kind of see that the more sides we add to this polygon, the closer we're going to get to that area of a circle. And so what we want to do is we want to take the number of polygons that we have to keep doubling it. And we also want to make the angle smaller and smaller as the number of polygons increases. And so what we could say is that the number of sides is increasing by a factor of 2. And our angle is always going to be the number of triangles that we have inside. So it's going to be pi over n. So this is if we have 8 triangles. And before, we had 4 triangles. And our total from before was 4 times 1/2 sine of pi over 2. And what we can see is that this value here is always half of that value. And so if we wanted to generalize this result, we could say that the area of a circle is going to be 2 times a number times 1/2 sine of pi over that number. And we want that number to get really, really big, so we apply a little bit of calculus and we say the limit as n goes to infinity, as n gets really, really large. So our 2's cancel and we just get n sine of pi over n, the limit as n goes to infinity, like that. And we especially want to focus on what's happening to our function as it gets really, really big. So if we zoom out, and we zoom out, and we zoom out, we notice that n approaches infinity. We recognize that that horizontal line is pi. So the limit of this expression is pi. This circle has an area of pi, like that. And that's how you successfully convert from one math constant that we know and love into another math constant that we also know and love.